Well, we're here to see Nathaniel's defense. Nathaniel came to Marquette in 2011. Can you hear? No?
It's going to the live stream people.
Okay.
Not the space.
Nathaniel came in 2011 as an undergraduate. He's probably held every job there is within the department, working for Dr. Park and myself in undergraduate research and senior design. And he finished up his undergraduate here, and now he's on his second bean, which is working on the master's thesis. So today he's going to present his master's thesis work, which is in support of the gas gun facility downstairs. Take people down there later, maybe. If you guys want to see it, it's downstairs. We'll take you to it after the defense.
Thank you. Hello, my name is Nathaniel Humanek, and I'm a master's candidate at Marquette University. And I'm here today to present my thesis work over the past 2 years, construction and characterization of a single-stage dual diaphragm gas gun. Before I begin, I'd like to make a couple of acknowledgments to start. First and foremost, the Defense Threat Reduction Agency, who paid for all of my work. Then to people, friends at Marquette University, including my advisor, Dr. John Borg, the whole of the Borg collective, faculty, and employees. You've all been a great help. Next, I'd like to thank the places where I visited during my thesis research, including Harvard, Georgia Institute of Technology, Sandia National Laboratories STAR facility, as well as my computing resources, U.S. Army Research and Development Center, as well as the DoD Supercomputing Resource Center. Lastly, again, I'd like to thank friends and family for being here. You've been really great and supportive, and I really appreciate it. The outline of the thesis today, I'm going to first go over a quick historical review, doing some ballistics, shock physics, gas guns, and then Marquette's role in all of it. I'm going to go over the construction of the gas gun, looking at the static gun components as well as the active gun components. Look at the modeling of the gun experimental behaviors, and then finally go over the conclusions and maybe some future work. Okay, so if we think back to prehistory, one would have to imagine humankind's first interaction with ballistics to happen something like this. Early humans, through observation or by happenstance, did affect or did witness a significant change in the local velocity of an object apart from themselves, and them not being an effector of this change noticed its impact. And that was the first experience with humans and ballistics motion. In other words, somebody threw a rock. Or, looking at the anthropological studies, it was perhaps a spear. Now, projectile technology has existed since at least 4,000 BCE in the form of spears, and this technology was eventually refined with the discovery of bows and slings, which were continually upgraded with the strongest materials of that time period. Bows give you that nice potential energy in which to store your energy in potential before letting it go as kinetic, and then slings give you a really long moment arm in order to really wing those projectiles around before you let them loose. Evidence suggests that the first gun that was ever produced was designed by Archimedes of Syracuse. Now, I couldn't find any old papers by Archimedes in the old literature review, but what I was able to find were some pictures of his gas gun in some work done by Leonardo da Vinci. And he said that Archimedes designed this gas gun, which was run off of steam, in the Battle of Syracuse in about 250 BC. Now, if this was true, it would predate the discovery of gunpowder by the Chinese in approximately 950 AD. Now, powder cannons developed from these early experiments with gunpowder by the Chinese in the form of fire lances found gunpowder to be an excellent means of propelling projectiles with significant energy. They eventually refined this approach and made cannons, which would eventually spread to Europe. And here we have a European cannon, one of the first pictures of that. And then Machiavelli would write in his Art of War, "There is no wall, whatever its thickness, that artillery cannot destroy in a few days," certainly of great military importance even then. So going through time, people are starting to think about what makes projectile motion and ballistics work. Aristotle, in his work Physics, presents some of the earliest theories for projectile motion, assuming that elements within the universe settle to a natural order. And he thought this order was earth at the bottom, water, air, fire, and then something called ether at the very top. And he would say, if you asked him about projectile motion, that if you took a rock, which was made out of the earth element, and you threw it through the air, it wouldn't like being in the air, and it would eventually want to fall to earth. So the projectile would move through the air, it would be very unhappy, and it would lose energy, and it would be very unhappy. And then after it lost all that energy, it would fall through the spheres of air and water to the earth in a straight line. So you throw it, it makes lots of motion, and then it falls straight down. Sort of a 1D approximation of projectile motion. A more two-dimensional view of motion was discussed by Galileo. Galileo's theory of parabolic motion was first published in his work Lo Specchio u Storio, which was written in 636 by a former student, the Jesuit Bonaventure Cavalieri. That same year, Galileo would expound upon this theory, his own theory, in his work Discourses Concerning Two New Sciences. Newton's Philosophiae Naturalis Principia Mathematica explains this motion with the idea of gravity. So it forms the projectile motion, and then that's explained by the gravity acceleration force. Finally, Johann Bernoulli in 1695 would formulate this theory of drag, which largely accounts for any discrepancies between idealized projectile motion and natural projectile motion seen in real life. As the behavior of guns became more consistent between rounds, great thinkers beyond Aristotle, Galileo, Newton, and Bernoulli would all try their hands at characterizing the behavior of projectiles. They would look at projectile shapes, firing conditions, etc. to try and explain what was going on. Manufacturers at the same time wanted to get in on the game. They downsized the cannon, made it more ergonomic. They had rifling in both the barrel as well as the projectile, making shots increasingly accurate. And as the shots became more accurate, you could use measurement devices such as the Bashford electroballistic chronograph, and you can create these ballistics tables, which provided immediate solutions for standard projectile trajectories in large guns and artilleries. So now we're getting into about World War I. The equations used to make these ballistics tables have modern versions in ballistics books today by J. Ingalls, R.H. Kent, and F.B. Piddock, whose ballistics equations is used in this work. So I used F.B. Piddock's equations for my theory. So ballistics, rockets, and calculators. By the end of World War II, projectiles were becoming rocket-propelled. You no longer needed a cannon to fire your projectile. And such computers such as the ENAC were created with the express purpose of computing these complex trajectories, making previous methods, hand calculation, big rooms with hand calculators, obsolete. As the computers became smaller and faster, these trajectories could be corrected on the fly. Now, with accurate methods of delivering projectiles to targets, scientists could then focus their efforts on post-arrival behaviors. These behaviors include penetration mechanics, which using the Rankine-Hugoniot jump equations shown here, as well as strength models and equations of state. These are actually the jump equations, not the Rankine-Hugoniot jump equations, just the simplified shock form. Were incorporated into the conservation equations to create modern ballistic hydrocodes, like CTH and some other Eulerian hydrocodes shown here. Now, even as the construction of these modern projectiles became more sophisticated, gas and powder guns still play an important role in the field. Gas and powder guns around the world are used for their consistency in testing penetration or impacts, creating new material types, and expanding our knowledge of material properties at high strain rates. Single-stage gas guns, like the one shown here, provide a cheap, clean, and safe, I guess less regulated because we're not using explosives, method of performing such experiments at the cost of lower projectile motion speeds as compared with powder guns. If you want to go for higher velocity, you can use a dual stage gas gun with 2 stages. Light gas guns can also offer the fastest projectile speeds of over 10 kilometers a second. You can see inside of this historical review, we were getting pressure velocities even in excess of 10 kilometers a second at some points. So what are these gas guns used for exactly? Penetration mechanics and material models and all of these things are in large part driven by strain rates. For the civils in the room, Instron testing machines are excellent for testing low strain rates as seen in civil structures. Hydraulic and pistons and Hopkinson bar tests allow for mechanical testing at moderate strain rates for most of the mechanical engineers in the room. And then gas guns. Now gas guns test up to very high strain rates, up to including shock loading at a mesoscale. So that's in the millimeters to centimeters range. I think looking at this whole field of mechanics, I think Mark Myers puts it best when he mentions that soft, free-flowing sand is effective against impacts of a velocity of a small caliber bullet on the order of a mile per second. But, on the other hand, a simple knife can defeat any sandbag. Clearly, study of both high and low strain rate interactions are in great importance to the modern engineer, but we're going to focus on those high strain rate mechanics. I've briefly tossed around the idea of shock physics, but I haven't really given a quick explanation of what it's going over. So let me give you shock physics in a nutshell. So shocks are propagating disturbances which travel faster than the local sound speed of a material. In general, the closer atoms within a material are packed together, the faster the information can propagate. You can see the stick figure poking a rod, and then you have the propagating poke, and then it finally pokes the sphere of death. As variables such as sound speed are approximately constant for a given material, energy in shocks can be stored in other terms, such as pressure and density. We can use equations of state to try and fix other things if we have some unknowns. I have a simplified seasons chart here. For example, if I knew that the weather outside had a humid climate and a hot temperature, I might say that it was spring. But if I only knew 2 of those, I might be able to back out what some of the other properties were. So if I knew that the season was fall and the temperature was cold, I might be able to guess that the temperature was really dry. Now, if you think back to high school chemistry, we know a really good equation of state. This is the ideal gas equation. And if we know 4 of these, we can solve for the unknown. We can also do post and pre conditions to figure out conditions of gases at different times. Now, for simple solids, these interactions have been well characterized. You can see I have some of the Rankine-Hugoniot jump equations, the simplified shock equations, and it's just like the ideal gas. You can see that we have a final state, we have an initial state, and you use them just like you would in a method called impedance matching, just as you would use the ideal gas formula. Of interest within shock physics is the phenomenon and behaviors that exist when different materials interact. So let me go over a brief history of Marquette's role in all of this. In 2001, we have Dr. Borg starting out his research into shock. He's got a paper on the fragmentation of liquid-filled cylinders. 1 year after his arrival, Dr. Borg was already busy. We already got Marquette's first 1-inch gas gun. And then we were already also simulating compaction of porous silica powder using hydrocodes such as CETH and KO. Moving a little bit forward in time, you can see that we're still doing some compaction of aviation brake powder, some compaction, doing some more hydrocode simulations. We have an epoxy over here, looking at equations of state to drive these simulations, and then an update to our in-house hydrocode simulation of shockwave structures without the use of artificial viscosity. Now we get to the area where I start to exist. When I came, I saw this cool half-inch single-stage gas gun, which was already in operation by 2011 when I appeared on the scene. Marquette Shock Physics Group just got a new addition to their computing capabilities with a ThinkMate workstation, which is really awesome. And I also spied inside of the shock physics lab and I saw the parts for a 2-inch gas gun. So I was really excited about that. And then we're starting to look at some things like compaction of materials, and we're looking at grain fracture here. Finally, we reach about present day. Right now we're working on granular compaction and pressure shear. Logan just presented a thesis on cylindrical explosives. We just finished up some work with sand penetration, and now we're looking at new techniques in order to pull data from our new gas gun that we're getting in. And then here's the current Borg collective as of today. Okay, so what's our motivation for doing all of this? The construction of the single-stage gas gun allows Marquette Shock Physics Group to compete on an experimental level with other international groups. Projects can go through now an entire project cycle with our group able to simulate, model, and test on campus. Current projects which require immediate attention include some shock interaction through granular materials, the behavior of earth materials and pressure shear, and then some dynamic compaction and sintering of powders. Additional projects in the docket include pioneering of the latest measurement techniques such as photon Doppler velocimetry and maybe some fast pyrometry if we get lucky. So who are we going to join? We're going to join this community right here. This is just a few of the gas gun facilities around the world. You can see the United States got quite a few gas guns here. Europe also has quite a few. We get a few from China, a couple in Japan, at least one in Russia, at least one in India, and then a few in Australia. But that one, if I can get the pointer, that one's going to be us right there. So now I'm going to go over the construction of the gas gun. The gas gun consists of several contracted components: the catch tank, the target tank, barrel, and breech. So catch, target, barrel, breech. These are assembled together with parts purchased from vendors with ratings ranging from absolute 0 psi, to approximately 10,000 psi G or 10,000 14.7 psi A. Several components are modified and manufactured at Marquette. So let me start off with the breech and barrel and move my way down the gun. So when we first got our breech, we looked inside and we found some leftover machining chips, and we were really excited about this because we knew that the breech was made out of steel, but we weren't quite sure exactly what steel it was made out of. And while these chips did not provide us with enough sample to do a Sharpie impact test or a Rockwell test or any one of those Intron testing machines, they were big enough to fit inside of our scanning electron microscope. Looking at the scanning electron microscope's elemental breakdown, we found the presence of chromium, molybdenum, magnesium, iron, and carbon, which were consistent with a 4100 series steel. Both the barrel and breech, based on literature reviews, are probably 4135 or what I think to be the case, 4140 series ordnance steel, which is consistent with the design of most gas guns. Now, attached to this breech, we have a barrel and a clear outer collar, and we can switch these barrels. We have one smooth barrel for normal impacts where the orientation of the sabot and the projectile don't matter, and we have a slotted barrel when alignment of the projectile and target is needed. Using the breech and barrel dimensions, we found a couple of the following properties. We did a fatigue strength analysis, and negligible fatigue strength effects given the frequency at which the gun is utilized. We probably fire at most maybe once a day at peak operating performance, but having the gun fire 365 times in 1 year is really pushing it. So I don't think fatigue strength is going to be an issue. And with careful handling and maintenance of the breech as well as the barrel with grease or sealer, we can prevent oxidation of the barrel, and it should last for a long time. Going through the safety factors of the whole system, I calculated a minimum safety factor of 2 with this inner collar controlling that safety factor because it's of a fixed width. And then you just have to make sure, the biggest thing is to make sure that you have the bolts attached as well as this outer collar attached to the breech, at least 2 inches on there. Inside of the barrel, we put a sabot. Sabots are material encasement that orient the projectile and prevent propellant gases from passing in front of the projectile, which would decrease performance. Sabots in general would separate from the projectile in flight, but this is not the case for Marquettes. It's not necessary. Sabots typically are manufactured with polycarbonate, nylon, or aluminum, and the weight and the length of this sabot can be varied to affect projectile speed and control when exiting the barrel. Finally, after we do every shot, it's really important that you clean out your barrel. We didn't have a pipe cleaner that was big enough to fit our barrel, so we got a long brush and a long rod, and then we should definitely sweep out the barrel every time we do it to ensure optimal launch performance. Once we go from the barrel, we reach the target tank where all the magic happens. The target tank houses the target plate, as can be seen here, and all the experimental equipment that's mounted onto there. We get fibers and wires that are all moved through this bulkhead, and then it goes through a 2-inch NPT port, leaving a second on the other side free for diagnostics expansion. I also have a ball valve on here on the 1/2-inch NPT port to allow the chamber to be quickly repressurized to atmospheric pressure if necessary. Every time that we attach the target plate, we want to do an alignment to make sure that this target plate is aligned with the barrel. And then you have to, before you put the target plate on, you definitely want to remember to put the light gate in there. Alignment for typical experiments is ensured in large part by this dial indicator. And then after the plug is inserted into the barrel, you can take measurements around the circumference of this. You plug it into this equation, and it gives you a milliradian output of your alignment. Inside the target tank, we have samples that are mounted to the target plate. And after placement of the sample, we use this blast shield, and we can put the blast shield over the target plate, and it fits snugly between the two light gates. And these slots in there ensure that you're able to get the fibers out from the front of the experiment, as well as light to pass from light gate to light gate so that you can get measurement readings. Attached to the target tank is the catch tank. The catch tank contains blast resultants from the experiment. And this keeps post-shot pressures below an atmosphere and prevents the projectiles from prematurely exiting the chamber. We hope that instead of the projectile exiting through the back wall right here, that it'll have in fact hit this impact plate, and the impact plate will dissipate the shock and prevent it from exiting. It's got a layer of rubber, and steel, just to make sure. After an experiment has been assembled, the blast shield is slid into place, and the catch tank is rolled forward. It's on a pair of rollers, which are hard to see, but it can be rolled forward and back so that you can button it up or get inside here and operate on your target plate. On top of the catch tank, we have a vacuum system. Here you can see a welder putting our mounting brackets on there, and our system is capable of pulling the test chamber down to about 50 millitorr. Moving over to the active components, after cleaning and mounting and aligning of all the statics components, a number of systems are required to operate the system, otherwise it'd just be a husk. The design sought to allow remote operation and manual override of the systems so that we could keep our researchers safe and also provide some fail-safe conditions. In order to control it, this is the brains of our system. A remote firing system keeps the researchers safe. You can see that they're outside of the building, and in fact, usually they'll work inside of a different room altogether. And in order to accomplish this, Marquette's 2-inch gas gun uses National Instruments data acquisition system, and then this is all piped from this room into the fluids lab via a single boosted USB 2.0 extension cable. The DAC system is convenient as it allows for data collection, for live system status readouts, and the option to send control signals and devices from a single software platform. In the event of electrical failure, the system ceases operation to prevent the gun from operating outside of the user's control. So here I'm showing just a brief electrical circuit. In general, what's going on here, this is from the electrical valve status readout. So you have status readout here. You have a cam that operates the valve, and then you have the logic board right inside here. To avoid signal contamination, we used separation using a 12-volt power supply to then go over to a 120-volt relay. And this would electrically isolate high voltages from the control system. Output and control is accomplished through two GUI options. We have a technical debug screen It shows you nice readouts about what's going on and if there's a problem. And then during main operation, I have a pictographic control panel which shows you an artist representation of the gas gun. You can see the chamber right here and the small chamber, large chamber, pressurization, release valves, just so that you can see what's going on from a visual standpoint. In order to pull stuff down to the low pressures, we have this vacuum system. The vacuum system allows the entire gun to go down to an equilibrium pressure with the room after a shot, as well as keeps the forward section of the projectile free of gas, which would slow it down. It increases velocity performances. Before firing, the vacuum safety valve, this valve right here, should be closed to isolate this gauge right here from the vacuum system, because if we have a shock that pulses up through this tube, it could mess with our pressure gauge, which is located up here usually. And then, after firing is complete, the remaining particulates can be scrubbed from the system using this line, which goes to a rough vacuum system that Marquette uses here. And we can just plumb that directly into Marquette's system, but before it goes into Marquette's system, it passes through this filter. As mentioned, 2 vacuums are used, Marquette's rough vacuum line, and then this rotary vane vacuum to reach a approximately 60 millitorr operating pressure. This is the operation of the rotary vane. You can see that these are little gas particles right here. We have a check valve over here, and then there's a little void space that opens up, pulling particles through, and then it expels them through this check valve up at the top. So that's the rotary vane pump. Vacuum pressure curves. So there are 2 vacuum gauges to allow for the monitoring of vacuum pressure in 2 ranges. So this one goes from 0 inches of mercury to approximately negative 30 inches of mercury, and that's the full range of operating pressure, but it doesn't give you the precision that you need at those low pressures. This gauge will tell you it's 0 pressure inside, but there's still a little bit left in there. So that's why we use this thermocouple gauge, which can give you pressures between 2,000 and 1 millitorr. These 2 gauges monitor system pressures as flow within the system transitions between the viscous and molecular flow. The equations here in order are the transferring pressure at which it switches from a viscous flow to a molecular flow, and then these 2 equations give you the viscous and molecular flow behavior. When we plot these here, the lines shown in red are the analytical equations that I found in a paper by Y. Senda, and you can see that our experimental data, you can see right here, this is the dial gauge, and then there's this break point. It's a point where we can't measure between the 2 valves, and then all of a sudden we get data from our thermocouple gauge, and it matches the theoretical curves quite well. Essentially, the difference between viscous and molecular flow is that in viscous flow, particles are really jumbled together and they're really close packed together. And then in molecular flow, the mean free path of any of these particles is just floating around in free space until it bounces against the wall. And those are a little bit harder to cordon in. Leaks into the target and catch tank chambers limit the lowest pressures attainable by the system. As you can see right here, we've got a little bit of a leak because it's fallen off of this molecular flow curve, even as it's switching between the 2 modes. So we use vacuum grease and special vacuum fittings to decrease these leak rates. Leaks are best detected using helium. So if you just spray helium around the leak, it'll reach a new steady state pressure, usually a little bit higher, and that way you can tell that it's leaking in that area. Going into the pressurization system, the pressurization system makes use of a Haskel pressure booster, which doesn't require any electricity in order to charge our system up. We have input air from the shop, and then we also have another system of air that goes also to the Haskel. So we use the same line in our lab to both power and use for pressurization inside of the Haskel. And after the Haskel, you get output to our distribution system. On this system, in order to control it, we're using this Max solenoid valve, and it just flips on, flips off, and it's also really cool because it's a critical component. It drives the system, and it's also a really good electrical fail-safe. Just in case things happen, electricity falls off, then this will close, and then that stops running, which is awesome. This is just showing you how the Haskel operates. You get charging gas going into the chamber, and then you get just these two really cool areas on which these gas pressure from the supply can pressurize these two gases. I also really liked this counterflow heat exchanger, which keeps the gases going into the second stage of compression really a little bit cooler. And then output, you get pressurized gas. While the system can be charged to shop air to about 10,000 psi in about 1,000 psi in about a half hour, booster performance is expected to slow at higher pressures. You can see right now it's a little bit linear. This is all the way up to 2,000 psi. But not only does it take a while, it's also expected that the pressure supply curve will probably dip down as we reach to some of these higher pressures. So a nitrogen or helium tank is therefore suggested for experiments where breach pressures are above 1,000 psi in order to give adequate charging times as well as optimal performance of the system. Pressure coming from the Haskel goes into this pressure distribution system. We have a high side, which goes to the large chamber, and then we have a low side, which goes to the small chamber, and then we have this other line right here, which is a pressure relief valve. This makes sure that any gases coming from the Haskel will never exceed 10,000 psi, which is the system pressure that the system here is rated for, and that's another fail-safe switch. Then we have a pair of regulators, this red and the green one over here. They allow researchers the ability to preset maximum pressures in the small and large chambers if you don't want to be glued to the screen on your GUI. Needle valves on the outlet coming from your system right here. When you want to bleed one of the valves can be set so you can decrease flow rate. There's different types of firing mechanisms that are available once you've charged up your breech. You have a fast-acting valve, which is just a valve that you open really quickly. A wraparound breech where the sabot holds back the air pressure, and then when you want the gun to fire, you just push the sabot a little bit forward, and then this will fill the area behind the sabot. And then you have a dual diaphragm system, which works off of pressure differentials between the two discs to fire them. Marquette's 2-inch gas gun uses this dual diaphragm design. After you exceed the burst pressure, you get burst disc failure. As you can see, here we have a Mylar disc, which has acceptable failure, nice pedaling on your disc there, and then there's no particulate thrown down the barrel. And then this one is a bad failure. We used a copper disc here, and it shot a plug down the barrel, and that was no good. So burst discs are usually these round plates of material. They fit in the pressure chamber, and then they break off. These high-pressure discs made out of aluminum and brass are usually purchased from Physics Application Inc. and are pre-labeled with the experimentally tested burst pressures. So we're going to use these Mylars for low pressure and maybe some of these for higher pressures. And now I can see that your faces are all glassing over a little bit, so I thought it's time for some gas gun jocularity. So, why did the gas gun suffer from back problems in the form of sciatica? It had a burst disc. That's gas gun here. Too long in the lab. So, with that in mind, let's go forward again. Design of metal burst discs. As it was previously mentioned, burst discs are either purchased and they're pre-labeled with a range of burst pressures that are tested in the lab. Robust analysis or a robust analytical equation for the pressures at which these burst discs would fail would be really awesome, but it was hard to find. In investigations, it was found that burst discs are created, as mentioned before, then tested and modeled in a finite elements package, such as ANSYS, before manufacture, and that's about the most that I found on burst discs for being analytically determined. Like, that's how you figure out what the pressure the burst disc is going to fail at. Analytically, I found one single equation by J.J. Rast, who noted in his hemispherical theory that a hemispherical disk might burst in rather linear curves, and then he showed some flat disks which would eventually balloon out to hemispherical size, and then they had this more curvy-like behavior. So it's kind of difficult. He tried to characterize it, and he came up with these couple of empirical equations, but these were valid for only steel burst disks, of which we had none. So I tried to do my own analysis. I tried to do it for the behavior of Mylar burst disks. Essentially, I said that the stress was going to be felt most strongly in this little curve right here, and as a burst disk went from a flat form to a hemispherical form, the area was going to increase, and that was going to be directly related to the thickness of the burst disks at final stage. So I came up with this formula right here. It's got a little squared term in there, but not it's pretty docile. But on kind of closer literature review, a formula of similar nature had been derived by Peter Barlow for cylindrical pipe walls, and his formula was really similar to my own. In fact, if you say that the radius of the disk is much greater than the thickness, this initial thickness term drops right out, and this simplifies down to this formula. So nothing groundbreaking on my part, I guess, but I did a thing. Plotting my theoretical formula, or this burst disk formula for cylindrical pipe walls by Peter Barlow, we can see that for the range of Mylar strengths, which are shown in blue, our experimental data is fitting pretty well in that range, at least for these low disk thicknesses. Now that we have tried to characterize our burst disks, we'll assume that we know what the burst disks will burst at a priori. So we'll have a range, or we'll have a burst pressure at which these burst disks will go. From here, one can begin an investigation of the burst disk system using a pair of 1/8-inch thick scored aluminum burst disks with a nominal burst pressure of 1500 psi. We'll say that's the pressure at which it bursts. So then you come up with this range, and this is a space in which you can figure out, based on a small chamber pressure and a large chamber pressure, at which pressure the gun will fire. So if we have a small chamber pressure here, we go up and up and up and up. Eventually it'll fire if we reach above 1500 psi. Now the stable range of operation would be a small chamber set pressure of maybe about 1000 and a large chamber pressure of about 2000. That's right in the middle of a stable range. And then if you want the gun to fire, you just start draining the small chamber burst pressure, and that moves this little pointer dot all the way over, and it moves into the red space, and the gun fires, theoretically. But that's only when you know exactly when the burst disks are going to fire. Now, it's actually more complicated than that. Most people give you a range over which they'll fire. So you have to plot your aluminum limits for the small and large disk, and that gives you this internal red square of actual stable operating pressures. And then I threw in an extra safety factor to give you an additional little operating chamber in which to work. And in fact, you can do it with pairs of burst disks. You can do aluminum Mylar or aluminum, and you can get a little bit of operating pressure range where you can run with two different types of burst disks. But in general, you're probably best off using the same burst disk in both chambers. So going over the dual diaphragm firing procedure, we start out with our breech. We have a large pressure chamber, a small pressure chamber, and this goes to the barrel. High pressure disc and a low pressure disc, and we'll assume that both discs have a differential burst pressure of about 500 psi. We'll start it both at 400. Neither of those pressures will burst the discs, and if one of these chambers bleeds, the gun won't fire. So this allows low pressure tests to be done to make sure it's operating correctly and it's all sealed. Upon successful leak testing, we'll raise this large chamber pressure up, and you'll notice that 700 minus 400, that's 300, that's lower than 500. And then 400 and 0, that's also lower than 500, so the gun won't fire. You bleed out this small chamber, 700, 100, that's 600, that's above 500, so this burst disc A, this high pressure disc, is going to fail. And that's going to let pressure from the high pressure chamber into the low pressure chamber. Now the pressure decreases a little bit, but it's still higher than 500, so that B, the low pressure disc, is now going to go. So it goes, and you have two open burst discs, and then the gas is going to go down, and the gun fires, which is awesome. Now, once it goes down, we got to figure out, maybe before we fire the gun, how fast the projectiles is going to go. Otherwise, then we're just guessing and firing the gun for fun, which is cool, but got to do this scientifically for some reason. Gas gun facilities typically use data from previous experimental shots. They have pre-done experiments, and they just pick it out from the, oh yeah, we've gotten results consistently at this pressure and before. Or they'll use programs like ANSYS and their CFD packages to determine muzzle velocity. These take time. Either you got to get experimental data to run from, or you got to run programs like ANSYS, and then you never know if it's going to be correct because you got to make your boundary conditions great. It's a big hassle. So using an analytical or empirical method would be really awesome. So this study compared a variety of derivations to ensure accurate velocity predictions. And then as we go through these different models, isobaric, isothermal, adiabatic, Lagrange, and Piddock and Kent, we add complexity. Some of the biggest complexity comes from the sound speed, because in nitrogen, we're going to be firing at velocities above the sound speed of nitrogen, which is 343 meters per second. We're going to be upwards of like 700 meters a second. And that means that information is going to have to travel, voids are going to have to travel all the way from the projectile down to the back of the barrel, and they won't be able to make it immediately. You're going to have shock waves in there, and then you got stuff from the back of the chamber all the way trying to make their way towards the projectile, and it's just a big old mess. You have these characteristics, and lots of work. But you do all that, you just turn the crank, and then this pops out. You get the gas gun velocity behavior. You can see that we have the isobaric, isothermal, adiabatic, Lagrange, and then some Piddock and Kent. This one in gray is for helium, which we may or may not use, and then nitrogen, which we typically use. And we get a range of gas gun performances. So we're operating right between the thrust, SSC, which is the fastest land speed vehicle on Earth, and then the Blackbird, which is the second fastest unclassified airline that's running right now. So if you want to take one of these, it's the second fastest, and we're operating right inside there, which is really awesome, really fast. And this presented curve assumes that the sabot is about 0.55 pounds or 0.25 kilograms. And then, since we can use this curve at different lengths, so we can solve this equation at various lengths of the projectile barrel, we can back infer velocities at different positions, and that allows us to get estimated sabot travel time, which is great if you're trying to set your oscilloscopes or figure out how long it's going to take for your sabot to get one side to the other. Non-dimensionalizing this, we can put the rest of our data on there, and you can see that our 3 data points that we currently have match well with the theoretical curve, which is this purple one, which is the Piddock and Kent model with a breach correction factor. Going a little bit into it, you have the velocity right here. It uses a modified sound speed relation. This is where most of the headaches come from, because your modified sound velocity is inside of this integral, and it's kind of messy. And then you use a quick breach correction at the very end to account for the fact that the breach is of a different diameter than the barrel. After the shot is over, we have the expansion of gases into the entire system. So you've got something that's 4.5 liters in size expanding into a chamber that's 2.5 meters cubed in space. And using that, even at peak pressures of a 10,000 psi, we have for air, nitrogen, and helium, we're reaching final pressures that are below atmosphere. For hydrogen, we get a little bit of a different curve. We get a post-shot pressure above atmosphere, but we probably won't be using hydrogen because it's pretty flammable, and there's other considerations, so it's a little bit of a hassle. Peak recoil force was calculated assuming helium gas and peak breach pressure of a 10,000 psi. And uses the change in gas and projectile momentum over the launch time, which we calculated before in the Piddock and Kent solution with that trapezoidal rule curve. We have some diagnostic equipment once everything reaches there. We have some PDV, which give you out velocity of different points. And then we have piezo pins and make pins, which will allow you to see time of arrival on different parts of your experiment. Going through the operations of PDV, light speed is constant. When the color of light is compared between non-moving and moving reference frames, its color or frequency changes. In physics, you can think of this also in terms of sound, I guess, with ambulances. This is how I like to think of it. You can tell when the ambulance is coming and when it's going. In physics, this phenomenon is known as the Doppler effect, named after Christian Doppler, after he noted the red and blue shifts seen in astronomical observations of stars. And to capture usable data, the light must be sent to a material surface, and then it's bounced back to the probe, and then you get one of these, which gives you voltage, which is the intensity of your signal over time. And then from this raw data, you do a fast Fourier transform, and you can bin these frequencies that occur, that are collected during a sample time. And you do this for various time steps, and then you pick out the top peak, and you can see here the top 0.5% of the data and the top 2.5% of data. You can see we have a curve. Note the y-axis right here. This is a down barrel probe monitoring projectile velocity, and you can see there's a very slight increase in the velocity of the projectile because it's just coming out of the barrel. And then you can tell where everything goes to pot because the projectile hits the target, and then all the lines are severed, and you no longer get data after this point because everything's like gone into the catch tank. But it's working pretty well. We also have a light gate. Instead of using a down barrel probe, we can also use this light gate. You get a series of 4 laser diodes, and they're each equally spaced apart. And as the projectile passes by each light ray, we can measure voltage drops. So here we have some normalized voltage, and you can see as the sabot tip passes by each of the lights, it blocks the signal, and it drops, drops, drops. You can use this time between each of those, along with those distances, to figure out projectile velocity. And so that measured velocity was really close with our expected velocity, our down barrel PDV measurement, and the light gate measurement. Another method of getting out velocities is reverse Taylor testing. According to G.I. Taylor, a well-respected fluid dynamicist and wave theorist, we can have a simple cylindrical rod, and when it impacts, it'll deform a little bit, and then you can use this awesome Taylor impact formula with your sabot, knowing its initial length, final lengths, and you can estimate projectile velocity. That was another awesome thing. After collecting the debris from initial experiments, it was noted that low velocity sabot deformation could be used, but at higher speeds, you started to get massive fracturing of the sabot, which means that your formula right here starts to lose a little bit of its potency. Finally, going into some future work, we got some cool experiments up ahead, some stimulating simulations, and then, of course, material smashing. Future experimental setups, we want to do some normal and conical impacts, some oblique impacts, and some shock sintering. So here we have one of our first experiments with shock sintering. It was used as a test shot. And then here was a pressure shear projectile and target. And some of our other researchers in the lab are looking into some cool results off of that. Especially these these oblique impacts, because you've got not only those longitudinal waves that you could easily see in our barrel, you also get these cool transverse waves, which are really awesome. When you want to take measurements like that, you got to use the PDV. And as aforementioned, it's all about light return. So for single probe measurements, light must bounce from the material surface back to the probe, no matter the probe angle. And so you use a retroreflective surface, and we like to use the actual material surface itself because there's nothing that tells you the material surface velocity other than the material itself when you're actually measuring it, which is awesome. These patterns right here were manufactured at Marquette, and then they are recognizable as their rectangular and triangular cuts suggest. They're nominally accurate, but if we need some extra machining techniques, I know of some good people over at UW-Madison who are doing some really awesome micro machining. Next, we need to work on alignment. So right now we've been aligning our targets using a touch method. So putting our two and trusting that our target alignment is the best, and then you get a post-shot measurement using the piezo make pins at the end. There are some other methods that we could use, including laser alignment, like those used by Harvard and Eglin, where you shoot a laser down, and then you have a optical flat, and it bounces light back, and you take measurements at the barrel, and then the target surface itself, the sample surface itself, and then you can see how good your angle is. You could use an auto-collimating assemblies like those in Brown. These are useful if you want to do anything other than normal impact tests. You can use these for oblique impacts, which we will be doing. And then another method proposed by myself, including a rotating laser alignment plate, which you'd be able to rotate this plate and then align two different targets, even if they're at a different angle. So if you move this a little bit off, it'll fall off of this detector plate. Then you can move one or both of these into alignment. Finally, we want to do some work expanding our simulation capacity. Due to priorities and time constraints, this research was only able to devote substantial time to simulations within hydrocodes such as CTH and KO. I did manage to run at least one simulation just for a simple flyer plate. And these codes have been workhorses within Marquette Shock Physics Lab and yielded many excellent predictions. While it's easy to use and excellent for material modeling, large deformation, CTH has difficulty modeling fracture, especially with individual grains. And so maybe a paradynamics code such as Paradigm might be the answer to that, adding another tool to Marquette's simulation toolbox. And then we have an artistic representation of future simulations. And so that's the end of my presentation. Thank you all for being such a fantastic audience. I think I'm in time. If you guys have any questions, I'd be happy to answer them. Thank you.
Just for the live stream, I'll come around if you raise your hand.
Or if you could come up and ask the question into the microphone,
well.
Appreciate it. Any questions?
I had one.
Oh,
I was just curious about, you visited many other facilities,
yes, sir.
right? Looked at what their facilities were like. What makes the Marquette facility unique in terms of capabilities that these other places may not have?
Okay. Marquette's facility is awesome because it's in such a great location. Other facilities that I've toured had really spread out facilities, and Marquette's really awesome because we've got the machine shop just up the steps. We've got excellent access to computer resources all on campus, and then we can also do quick turnarounds of creations of experiments. That's really awesome for us, that we can do all of it within our group right here at any point in time. Other groups, they have to wait for machinists. They have to wait for, they have to travel across campus or something like that. It's all centrally located here, like that.
Could I ask you to raise that?
All right. Wow, you did. Is it master thesis? All right. The couple things that when I read your paper draft, the thesis draft, that motivation. Number one is this system is cost effective.
Yes.
And reliable.
Yes.
Okay. Anybody built this kind of system before? Any comparable design or construction? And you said the characterization.
Mm-hmm.
So I didn't see that anybody did. You are the alone. You are the pioneer in building.
No, not. I took the best pieces of hardware from every other gas gun facility that was around the world, and we tried to put it into our gas gun.
And how much cost effective in terms of like I said?
You don't have to buy permits for explosives. It's you get all of the energy you need right from the building. We just use gas, and that's mostly what I was talking about there. Gas guns, light gas guns, are awesome as opposed to putting up together a full-scale test or using explosives where you have to do a lot of cleaning. Cost-effective being in terms of once we have the infrastructure in place, there isn't a lot of upkeep cost other than the experiments themselves.
Okay. So, and then, sorry, anybody ask a question? Okay, I'll stop if anybody. You said performance. Performance is in terms of what? The energy in, energy out. Actually, the energy in to push the, the projectile, what do you want to call the, and then energy out and a target arrived. Did you have a chance to estimate total energy in, the high pressure push, and then efficiency, in other words?
I don't think I was able to do that analysis, but an answer sort of along those lines would be the longer the barrel is, the more energy you'd be able to transfer from the from the gases into the projectile. So longer and longer barrels, you get more and more efficiency. But our shock lab is kind of more constrained in size.
Yeah, quantitative because of this that Dr. Borg started with 1 inch barrel and then ½ inch, and then you did the 2 inches, right? And then with the lens, and then just when I was reading, it's kind of why 18 feet long, I don't know, 9 feet long, why 2 inches diameter. That may be related to the performance of the light gun.
Yes, right? Definitely.
And how about the shock wave? And then let's say usually the plane travel with the Mylar #1 and kind of very strong noise. So how do you handle that noise?
All the gases in front of the projectile are in vacuum.
Vacuum?
Yeah.
So they absorb.
So you just get bouncing of waves around inside of the barrel, but actually when the gas gun goes off, it's more of a low frequency disturbance, more like a that you can actually feel rather than an actual loud bang, because you're exploding a rocket in space, for example. Do you hear a rocket? If a rocket burns in space and you also happen to be in the space, do you hear it?
Yeah, that's why. Anybody question?
Well, what did you say? What, it's 10 tons, right? 10 tons
10 tons of recoil force.
Yeah, where you've got it connected to the ground there?
Yes. And that's a dynamic load rather than a static load, which would be even more substantial. But it's a dynamic, just like one single pulse at peak.
So you built that well, right? Down there, those bolts?
Those are bolted to the ground. It's not just for appearance's sake.
Good.
I'll have 2 more questions, and I will just. Okay, first thing that you did, you designed, you constructed, and then you. Is that am I correct?
A number of components came pre-manufactured with designs already done by places such as Physics Applications Inc. And I did a double check analysis in my work to make sure that
you designed the whole system, right? So in my opinion, the title of the thesis is like a design and construction of this system. Okay, system, right? Number of components, right?
Yes.
Static and then active components, and then it's characteristics or characterization. What do you call?
Yeah,
and then when I read the title as a construction and characterization of gun. No, system. I think you build the system.
Okay.
Right? Am I right? And then one last question is about the what is it? Okay, how many different operating conditions you can handle with this system? Seems like I saw only one operating condition, like 10,000 psi.
That's the maximum pressure that you can put into the system.
So what if you change the operating conditions, like a pressure, maybe 5,000?
You can do 5,000 psi. You can do 1,000 psi. We've done shots, I believe, at 300 psi all the way up to at least 1,000 psi.
So possible, huh?
Yes, yeah. You can fire at a range of pressures as long as they're below 10,000.
So last one more, sorry. What you, according to your experience in designing, construction of all the system, what are the key components, the static and active system, you can say? Key components, which means affecting the whole system.
Affecting the whole system, you really need to be aware in each of the systems what sort of, I guess it comes down to, like, since they're vastly different operating pressures, you have a high pressure side, you've got a medium pressure side, and then you've got a really low pressure side. So you got to make sure that you're using the right components for the right areas. Otherwise, you lose system performances. For the medium pressures, you got to use NPT. For the higher pressures, you got to use like swage lock components and stuff like that. And then for low pressures, you really have to make sure that you're using fittings and types of connections that are good to operate at those pressures. Most critical of the entire, I guess the star of the gas gun show, if that's what you're asking, is this breach, because it's the place where we're dumping all of the energy to begin with. It's the place where we're storing all the potential energy to make our experiments happen. If anything fails, you gotta make sure that this place is really sealed off, and it's a gun. You gotta handle it with safety.
when you were estimating muzzle velocities,
Yes,
you
sir.
essentially use work energy methods to do that.
Yes.
How did you either measure or guess at the friction between the sabot and the barrel?
The friction between the sabot and the barrel, I thought it was rather negligible looking at all the different methods that were out there. We did note that friction did play a bit of a role. And in order to combat that friction, even though no direct analysis was done of that, especially since the projectile is traveling at such high velocities, it's really hard to pick up the friction factors there. We know that you really have to grease the projectile before you put it in there. I think my grandfather was talking to me one day, and he was like, back in the day, you would grease your bullet before you'd put it in the gun, and that way it would fire longer and faster. So just make sure to lubricate your projectile before you put it in the business end of the barrel. It's always a good thing. Lubrication. Yes, sir.
So, this gun in the basement, we are here at Marquette University, Jesuit University. So how do you see, from the outsider,
Yep.
wow, you got this giant gun.
Mhm.
How does the gun support the mission of the university, care for the whole person? How does it fit in general?
So yes, the gun at first appearances looks like it's directly related for military applications. But it's also meant not only for penetration and impact studies like that, but it gives you a greater scientific appreciation for the behavior of materials at extreme conditions. And that's something that you can't do with any other type of experiment. These experiments are pointed at samples, and within these samples we can figure out more of the operating mechanics behind materials within the universe, which is really awesome. I believe one of the best things in the world is to be inquisitive. I mean, we were put here on this earth to tend for it and care for it, and by looking at materials in depth, even in cases that are extremely high pressure, high temperature, high velocity, and those can be used as tools to do bad things, but you can also use those tools to do good things as well. It goes a little bit off the topic, but it could be considered like nuclear fuel. You can use it in a bad way, or you could use it in a good way. A good way would be to power the world with clean energy. With this, a bad way would be to use it in warfare or something like that, and maybe protect people's freedoms, which might be in a bit of a gray area, morally speaking. But then you also can use it to discover more interactions regarding the most basic elements in our universe and push our knowledge and appreciation for the world that we live in further.
Well, if we have no further questions, I guess we'll ask the audience to.
Are there any people on the stream, David, that have any questions?
Oh yeah, maybe someone from the outside.
Check the outside and see whether we have any phone callers in. Or... Okay. Nope. Apparently no questions out there.
So yeah, we'll excuse the audience and just give Nathaniel one.
Thank you.